Assignment 2 is going to be a really nice review with just a little bit of new information. We're basically going to cover all the different types of functions that we covered in Algebra 2. So you may want to have your parent graphs out so that you can review, kind of make connections between what you learned last year and what we have on this piece of paper. Okay, so your essential question: what are the types of functions? And not only do you want to know what they are, you also want to know any special things about them, any special characteristics, or how to differentiate between them, what their graphs look like. But I'm not going to write a really long essential question. And then my other piece of this is, how do you use Boolean variables? That's the new piece, and that's pretty simple, and you're going to use your calculator for that. So starting with a couple of definitions, just simple review. These are on page 8 in your textbook. I'm just going to copy them straight out of there. So a relation is any set of ordered pairs. So it doesn't have to be a function, right? And maybe you're thinking to yourself, okay, I know how to tell if something's a function. But this could be any set of ordered pairs, whether it's a function or not. Function is basically a set of ordered pairs for which each value of the independent variable in the domain has only one corresponding value of the dependent variable in the range. Okay, so let's go ahead and write. I'm going to write down that whole definition. I think that that's important. And I think that, now that we're in pre-calculus, we should have some of this vocabulary. And I'll say independent variable, that's usually x, in the domain has only one, this is the key, corresponding value of the dependent variable, which we usually think of as y, in the range. So I did a lot of copying out of your book. I wanted it here so that way we could highlight it. I think that that's pretty important. And again, this is all review. Okay, so all of these functions you already know. We went over these last year, and you have them in your parent graphs. Okay, so polynomial functions could be any degree, usually starting with x cubed or higher. So this is a polynomial function. There's a little note here, a, b, c, m, and n basically are constants or coefficients. So you can see here I've got coefficients like a to the n minus 1. The n and the n minus 1 are like what terms they are. So they go with the exponent on your independent variable. So for example, if this was x to the 4th, then this is the coefficient that goes with x to the 4th. If that's x to the 4th, then this is x to the 3rd, x squared, and so on. Okay, so that's basically your general equation. I think that that's important, but luckily I copied it first so we don't have to actually write it down. Okay, so, and it says here verbally, so f of x is a polynomial function of x. So for example, and I already went over this, if n equals 3, then we've got a cubic. If n equals 4, then we've got a quartic. It could be n equals 5, and so on. This is important, the features. So the graph crosses the x-axis up to n times. We went over that last year. And it has up to n minus 1 vertices. Okay? The domain is going to be all real numbers. So those are a couple of important things. Quadratic function. Okay, so this is probably, you've basically been learning about quadratics since Algebra 1. So we've got the quadratic function. Okay, and that's your general form in standard form. Okay, and we know that the graph changes directions at one vertex. So we've got one vertex. Domain, all real numbers. And you can highlight more. I'm just highlighting some stuff that I think is important. And stuff that, I really, really want you to understand. And I kind of feel like the domain is pretty obvious, but you're more than welcome to highlight that if you think that that's something that you don't already know. Linear function, again, something you've been doing since probably 7th grade, I'm imagining. General equation where you've got a y-intercept and a slope, which is also looks like this with the m. Always going to be a straight line. It's got a constant rate of change. I should put changes at a constant rate. There you go. That's your slope, right? That constant rate of change. Now, direct variation is something that you probably went over in Algebra 1. I don't tend to make a big deal about it, but a direct variation is, it's a linear equation that basically starts at 0. So your y-intercept is 0, constant rate of change. So I don't feel like this is an extra one that you need to put in there, but it is good to know that there's a specific name for a linear function that has a y-intercept of 0 and has a constant slope. So then we have the power function. So the power function and the exponential function, these are very similar to one another. The power function, the general equation is a times x raised to the b. So your independent variable is your base, whereas in an exponential function, your independent variable is your exponent. So, again, they're super similar to one another, but something that you should know about power functions, and it's not a huge deal, is just that in most real-world applications, the domain is going to be, so like if we're thinking about time, you're usually never in negative time, right? So your domain's always going to be greater than or equal to 0 if b is greater than 0, and x greater than 0 if b is less than 0. So exponential functions, the big feature here is that the graph crosses the y-axis at f of 0 equals a and has the x-axis as an asymptote. So that's pretty important. And then we come back to that word asymptote. And remember, this is just, we're talking about the parent graph. So as you do your shifts, that asymptote could potentially move. Inverse variation function, also known as a hyperbola. I'm going to write that over here. That's the shape of the function. So basically, now you have two asymptotes. So both axes are asymptotes. Okay, and you could have, so usually you have them in opposite quadrants, so where they're diagonal from each other. And here, in this example, like for example, 1 over x squared, see how you have that squared down in the bottom? So if n is even, you're usually going to have them in quadrants that are right next to each other. Oh, and a good point to make is usually, again, for most real-world applications, you're going to have a domain greater than 0, so you're just going to use one side of these functions. Your general equation for these are usually f of x over like 1 over x or some constant over x, and then or f of x, you'll have some constant over x to some power. So last year when we covered these, we went over if we had a constant over a linear. So for this one, this is f of x equals a constant over a linear. Or another way that we wrote it was f of x equals some constant over x minus h plus k. Right, because these were going to be your two shifts, right? So that tells you where your asymptotes are then. So you know that your vertical asymptote is wherever the denominator equals 0, okay? So vertical is going to be basically wherever x minus h equals 0. Maybe I'll do this. And then your horizontal asymptote is wherever whatever your horizontal shift is. So your horizontal shift being wherever your x-axis has been shifted to. So it's going to be wherever y equals k. Okay, and then we have rational algebraic functions. So this is where you have a function divided by a function. So when we did this last year, we always worked with like a linear function over a linear function. So we would have something that looked like and we found our asymptotes in a similar way. So our asymptotes so the vertical function was going to come wherever it was undefined. So again, setting that denominator equal to 0. And then our horizontal came from the slope. So basically we set the slopes over each other. A divided by C. And that would give you your y value. Now, linear over linear isn't the only type of rational algebraic function, but for now that's enough for us. And it does say here that a rational function has discontinuity. Now, discontinuity means you have an asymptote or maybe even just a missing point. Here you have a point that is missing, and we call that removable discontinuity. Okay, and we'll get to that. That's more calculus terms. And it says that that discontinuity is always going to be wherever the denominator equals 0. So that's the same thing as that vertical asymptote. Setting the denominator equal to 0 is always going to have you find that. And then you could also have that horizontal or other asymptotes, and so that's where this horizontal asymptote would come into play, but just for linear over linear. All right, moving on to Boolean variables. So I gave you a definition here. It's also in your book. There's a lot of information here on Boolean variables, but basically we're able to restrict our domain. So Boolean variables allow us to restrict our domain. In the calculator. Now, Boolean variables are actually used they're used in computer science. That's how our computers actually communicate. So a Boolean variable is a variable that has a given condition attached to it. If the condition is true, the variable equals 1. That's a true statement. It turns on. If the condition is false, the variable equals 0. So that's a false statement. It turns off. And that's basically how our computers communicate, is using zeros and ones, or Boolean variables. Well, in our calculators, it's a little bit different. And there's some great information here. This is page 11 in your textbook. But basically, Boolean variables are going to let you plot a graph using only part of the window. Okay, so that's how we restrict our domain. So for example, if I wanted to restrict my domain between 3 and 10, okay, I'm going to have to divide out all the numbers between 3 and 10. So let's see. A Boolean variable was named for George Boole, an Irish logician and mathematician. And this was in the 1800s. And like I said, it equals 1 or it equals 0. And basically, this is how you do it. In your calculator, you basically just take the equation like normal, plug it into your y equals screen, and then you divide out what you want, where you want to restrict your domain. So here we wanted x being greater than 3, greater than or equal to 3, and x being less than or equal to 10, which is that. Okay, and so we basically just put that into our calculator just like this. You divide it out. Okay, so in this example, if x is between 3 and 10, the 26 and 3x plus 26 is divided by 1, which leaves it unchanged. So we actually get to see the graph. If x is not between 3 and 10, the 26 and 3x plus 26 is divided by 0, and the grapher plots nothing, which is super, super cool. Okay, so that's a little bit of information on Boolean variables, and then I'm going to show you how to do them using your calculator. So go ahead and get your calculator out. Okay, so I pulled my calculator up. Hopefully you got your calculator out. One thing that you need to know when we're doing these Boolean variables is that you are going to always, in order to find the inequality sign and in order to find the and, you're going to need to use second math on your calculator. So this is going to give you where the inequalities are. And then from there, if you go to logic, that'll give you the and the or. All right, so example 1, we're going to plot the graph of this quadratic equation, and we're restricting our domain from 0 to 4. Okay, so in our calculator, we'll do y1 equals, we'll do negative x squared plus 5x plus 3. And then we're going to divide out the Boolean variable. So we're going to put, and you can't write it just as it is. You have to actually make two separate statements. So we know that x needs to be greater than or equal to 0. And we also know that x needs to be less than or equal to 4. So that's exactly how we're going to put it into our calculator. Okay, so. All right. So I just typed in the function. Now I'm going to divide it, and I'll put a parenthesis in there. I'm going to do second math. So that gets me to test, and that allows me to use these inequality symbols. So it's a greater than or equal to 0, greater than, oops, I didn't put an x in there. Well, that's not going to work. Let me try that again. So I'm going to put x, second math, greater than or equal to 0. Now I also need an and in there. So that's going to come from second math, and you go over to logic, and is number 1. And now I need x less than or equal to 4. So I'm going to put in another x. I'm going to go down to less than or equal to 4, and I'm going to close my parentheses. Now before I graph this, I should probably make sure that my window's pretty standard. I want to see this in between 0 and 4. So I'm going to go to, oh, actually, let me do a zoom. I'll do a standard window. Uh-oh. Let's try that again. Zoom. Let's try standard. So the problem whenever I get invalid dimension is usually because I've got plot 1 selected and it shouldn't be. So let me see how I unselect it on this. Should be able to. There we go. So none of those plots should be selected. Okay, now it should work. So hopefully if you've ever had that issue where you get invalid dimension, you know to go up to your plots. Okay, so I'm going to go back to Zoom. I'm going to try standard window. And you can see that this is just graphing it when x is from 0 to 4. See how it stops? Otherwise, this parabola would have gone all the way until off the screen, right? So we'll plot this on our paper. You'll see that you can see where I erased. I started and it went way too high. So I want to make this a little bit further, a little bit lower. So at 0, that's pretty easy to see. I'm going to be at 3. And I can plug in the rest of the values pretty easily, or I can go back and use my table, which I'm going to go ahead and use my table. And I set my table so it starts at 0 and increase by 1. So at 1, I'm at 7. At 2, I'm at 9. Now at 3, I'm back to 9, which means that my vertex is somewhere between 2 and 3. And we'll locate that next. And then at 4, I'm down to 7. So to find my max or min, or to find my vertex, which in this case it's going to be a maximum, I'm going to do a second calc. I want to find my maximum. Okay, I'm left bound, right bound, and then best guess. So it looks like x is about 2.5 and y is just above 9. Maybe like that. So drawing this graph would look something like this. Okay, and we're going to give a range for this. So our output values, well, y is going to be somewhere between 3 and at 4 we're at 7. All right, and then the next thing we need to figure out is find a pair of real-world variables that can have a relationship described by a graph of this shape. So, I mean, there's a whole bunch of things. Maybe you have fireworks that you start off at 3 feet. By the time they reach 4, or after 4 seconds, maybe they're gone. They've evaporated. Okay, so that's one example. Let's see. Your book. Let's see what they give, because I just basically took this example out of your book. Could represent the relationship between something that rises for a while and then falls, such as a punted football's height as a function of time. So that's the example that they're giving. And you can think of anything else. A rocket, I don't know. There's probably a million things. Any kind of sport that has a ball, you could definitely use that as well. Okay, so that's using Boolean variables. And last example, example 2. As children grow older, their height and weight are related. Sketch a reasonable graph to show this relationship and then describe it. Okay, so that's example 2. So, as children grow older, they get taller, right? So I guess the first question is, what's my independent and what's my dependent variable? Well, as they get older, yes, they also get heavier, but really, they definitely get taller. And the fact that they get taller is going to increase their weight. Okay, so I think I'm going to have my independent variable be height, and my dependent variable be weight. How about I'll write it this way? Now, when we are born, we are not 0 pounds. Okay, so, and we're not 0 feet or 0 inches. So, you know, I'm going to be born and be somewhere in here. Now, as I get older, you know, it's not a linear. I don't grow the same amount every single year. So it's not necessarily linear. And as I grow the same amount, I'm not necessarily weighing, or sorry, as I grow different amounts, I'm not necessarily, my weight's not increasing by a constant. Okay, so this is not a constant rate of change. So it might be something where, you know, at first I start growing slower and slower and slower, gaining weight slower and slower and slower, and then kind of shoot off until I'm an adult. And then it ends. I don't keep growing. Well, I don't keep growing my height. Your body weight may keep growing, but then that wouldn't be this relationship here. Identify what kind of function has a graph like the one you drew. Well, this is an example where power and exponential are different. So, you know, you can say, oh yeah, this looks like an exponential function. But this if this was an exponential function, it would keep going through the y-axis. I don't start at 0, 0, right? When I'm born, I have a height, I have a weight that are corresponding to each other. So really extending this graph doesn't make any sense this direction. And it also doesn't really make any sense in my adult direction because I don't keep growing taller. Actually, if this was going to be accurate, I think people start shrinking as they get older. But we won't even try and make it that complicated. So because we never end up with a 0 height or weight, our values of height and weight are always greater than or equal to, or are always greater than 0. And so we have a power function. This is going to be a power function. But yeah, you could say an exponential function where your domain is restricted. You could do that too. They'd be really similar to one another.